essentially resume from where we were. So we have essentially 2.5 weeks before the midterm. So we need to cover quite a good amount of material. But of course, as you can see, that we are not trying to rush into it. We are trying to explain the derivation of Navier-Stokes in as much detail as possible. So we will go back, and in today's class, we will be completing our derivation of the Navier-Stokes equation, which is reasonably straightforward from the point that we have left. The second thing that we will do is to describe this equation in as much words as possible. You'll see that there are a lot of different interesting properties just looking at the equation that we would be able to understand or maybe able to make out. So that's the second sort of part, or second thing that we want to do in there. And finally, then we'll close this topic and move on to a new topic, which is on tensors. Okay, so this is the plan for today's class. So we can start by recalling a few things. So recall that we had derived our Cauchy's equation. So if I try to write out the x momentum equation, so these are the terms that we have, is equal to, we saw that this equation is written in terms of derivatives, in terms of stresses on the right hand side. So these are the terms that we had in our equation. And looking at this equation, this is our Cauchy's equation, if you recall. So we said that this equation, with all the stresses as appearing as unknowns in this equation, has too many unknowns. Okay, we have the, similar to the x momentum equation, we have the y momentum equation, the z momentum equation, and the conservation of mass. Okay, and we saw the number of variables is far more than the number of equations that we have. We also realized that at this stage, we have not said anything about the fluid. What type of fluid are we working with, are we dealing with? So that is, and we also realize that we don't see any appearance of pressure in all these cases. So that's when we brought in the constitutive relationship. So this is what we had derived in the class, 2 classes from now, and this is what we derived in the previous class. So in the constitutive relationship, so these additional stresses that that are appearing have to be now written in terms of other variables. And we saw that we can write out sigma xx as minus p plus 2 mu dou u dou x minus 2 by 3 mu times del dot velocity u. Okay. So this is my velocity u, okay, or let me just use velocity vector v. Okay, so this term itself was dou u dou x plus dou v dou y plus dou w dou z. Okay, so this is the equation that we had gotten from the previous class. Okay, now, and of course for sigma xy, we said that this is equal to mu times dou u dou y plus dou v dou x. Okay, and if we are able to find out one component, we can find out the other components by a suitable change of the variables. Because there is no preference for the x direction, we can write out the same equation along the y and z direction by interchanging u and v. So this is the point that we were in the previous class. Okay, are there any questions here from how we got to these equations? So I hope the derivation of what we have done is very clear. Okay, and again, we would like to emphasize that till this stage, there is no assumption that we have made. The first assumption that we have actually introduced is through this relationship, which is relating the stress and the strain. Okay, this we said is now belonging to a Newtonian fluid. Okay, where there's a linear relationship between stress and rate of strain. So this is the place where we have introduced this this information that we're dealing uh, with the Newtonian fluid. So that means if you're not dealing with the Newtonian fluid, so you can come back and change this equation, but the other Cauchy's equation does not change. Okay, Cauchy's equation is like a very generic equation. We know, we again recall that it was derived from the Newton's law of motion, okay, where we had mass times acceleration, which is all these left-hand side terms, and all the forces, which are our stresses, and the body force terms appearing on the right-hand side. So this is as generic as, let us say, the Newton's law. Okay, so there is no, I mean, whatever condition this is valid, this is valid. Of course, one special case we said that we are not allowing the mass to vary. We are not allowing, or we are not accounting for the change in phase, change in chemical reaction, or the possibility that there can be a chemical reaction and nuclear reaction. So those are the type of things that we have excluded. So again, this is where we are. Okay, so as far as these three conditions are met, so as far as we are talking about, let us say, a single phase, or even if there are, so we are talking about, let us say, nitrogen or oxygen or water, or we can even be talking about mixture of these gases and so on. So all these cases, these equations are absolutely exactly applicable. Okay, so there are no approximations anywhere. So now we are going to get to the Navier-Stokes equation by substituting and again I would like to point out that this Stokes, just like in Reynolds, okay, comes with a S. The name itself has an S in there. Okay, so it is not S apostrophe or in plural that is being used. So it's Navier-Stokes equation with an XS in there as well. So now what we are going to do is substitute these constitutive relationships into the Cauchy's equation of motion, which will give us the Navier-Stokes equation. So let's do that. And you can note that we are writing out in 3D right now. So I think last time we were trying to do this step in a little bit of a hurry and we were making too many mistakes. So we are just doing it once more. So you can see that all these three terms are being generated by taking the derivative of the sigma xx term. Okay, so we get all these three terms from there. Now we have to take the derivative of the stress terms. So we get dou y of mu, dou u, dou y, dou v, dou x. Okay, plus rho times fx. Okay, so this is the equation that we have, and you can say that this is right now the most generic form of the equation that we can derive. This is only restriction is, what is the only restriction? It's a Newtonian fluid. It's corresponding to a Newtonian fluid. Okay, there is no other assumption that we have made. So now we are going to simplify it to a few cases. Our first case, maybe it's a compressible and incompressible, something that we had introduced in the previous class. So, okay, now we can look at these equations, and there will be other equations like this. And along with the mass conservation equation, which we are going to write now, which was like here, dou rho dou t by dou x of rho u plus dou by dou y of rho v, dou by dou z of rho w is equal to 0. So this is the mass conservation equation, and we have three such equations along each of the three directions, which are your momentum equations along the x, y, and z directions. So these set together sort of forms the, I mean, we typically call the momentum equation as the Navier-Stokes equation, and this is a continuity equation. So these set together of four equations is what sort of constitutes my complete set of flow equations. And we are not accounting for energy as of now, so we are not putting in any temperature. There is no, the variable temperature, for example, is not here for now. And at once more, we can look at what are the variables and what are the, how many equations are here. So variables you can see from these equations, maybe start from the continuity equation, that's always a better thing. And that is always clear because if you look at these two equations, this is a far easier, simpler looking equation as compared to this equation. And remember that we have not even taken the derivatives yet. Okay, once we take the derivatives and expand out these terms, there will be a lot of terms that we will be looking at. So it's a good idea to start looking at this term from the continuity equation. And the continuity equation gives us that the variables are rho, u, v, w. We have already discussed these variables before. And you can see when if I go to this equation now, the only new variable that I pick up is p. Okay, there is no other new variable introduced here. Mu is supposed to be the constant, some viscosity. Okay, we have put density as a variable, so we are sort of in a compressible frame. We are not saying that we are restricting it to an incompressible flow yet. Okay, but on the side, on the right hand side, we see this body force term Fx, and this body force term, as we said, is supposed to be known to us. So we have 5 variables, and what are our equations? So we have already talked about one momentum, one continuity, 3 momentum equations. So we have 4. So one continuity, there's 3 momentum. Now what else do we have here? So we are still short of one equation. So what is that equation now? That's the equation of state. So plus 1 equation of state. Now this equation of state is a little bit tricky. So we would like to explain this, when to use the equation of state and when not to use the equation of state. Okay, so you can see as of now, we have a closed system. We have 5 variables and 5 equations. Okay, so this is a closed system as of now. Okay, and this is the generic equation, generic thing that we have, and which we call it as the compressible equations. These are the compressible equations, and that we have. Okay, now one thing about the compressible equation, if you are going to compare that, you can see that the left hand side of the equation is exactly the same as the incompressible equation, which we have not explicitly written, but we will write that. Okay, but the right hand side is where the difference lies. Okay, and which term? You can see that everything else is the same. This is the additional term that is going to appear on the right hand side. Okay, everything else is the same between the compressible and incompressible, and we will do that in a minute. Okay, in fact, maybe not exactly, but okay, we will see exactly how things simplify. But the bottom line is the left hand side of the compressible equation and incompressible equations are exactly the same. The right hand side is where the differences would lie. Okay, so this is now we are going from a compressible to an incompressible formulation. Any questions here? So compressible to incompressible. Okay, by the way, what do you mean by equation of state? What's an example of equation of state? Ideal gas law. Okay, PV, P is equal to rho RT. So now when we go for, so incompressible essentially means that rho is constant. Okay, and we would note that we are not putting any restriction on the Mach number. We are simply saying that density is a constant. Okay, now if density is a constant, and what it mean by, again, we are thinking of density being changed because of the flow itself. We are thinking of density as a flow property. And if density because of the flow itself is changing, then it is not, we are not going to satisfy this condition. Okay. So now we can see that we can go to the continuity equation and see that if density is a constant, the first term goes away, and the remaining terms I can pull out density outside the derivative, and which I can remove further. Okay, so I'm left with dou u dou x plus dou v dou y plus dou w dou z is equal to 0. So this is the continuity equation that I get now because of the incompressible assumption. Now, if I look at this equation now, I can recognize that this del dot v term, this is nothing but del dot v is equal to 0. This is my continuity equation. So that means I can go back to that equation and I can make certain simplifications. Okay. So that simplification would be that on the right hand side. So I will just write out the right hand side is minus dou p dou x, plus I will also assume for now that viscosity is not a function of space. We have discussed this point in the previous class. He said that we have already seen that viscosity could be a function of pressure and temperature. Okay, pressure we have already eliminated. It could be a function of temperature. Okay, in fact, we found that, if you remember our first or one of the homeworks, or maybe the first homework, where we saw that viscosity is a very strong function of temperature. I hope you have plotted it and you have realized that it is a very strong function. So some comments that you had to add, the comments are to sort of realize that what is the magnitude. So something is varying, it can vary by 1%, or something can vary by 200%. Okay, so it's a very large change is what you were finding. You would have found, I hope, when you were solving that, doing that problem. So, but here we are not really bringing in temperature anywhere. So we can say that, okay, but this is not in general. I'm just saying that this is sort of a special case now. So again, we are introducing some sort of an assumption. But if you don't want to introduce that assumption, you can work with this form of the equation. Okay, there is nothing. I mean, but it does simplify. It helps to simplify if we are able to take out or to assume that viscosity is not a function of space. Okay, my next term is gone. Okay, for my next term again, I can now take out mu times dou to u dou y2 plus mu times dou to v dou y dou x plus dou by dou z dou to u dou z2 plus mu times dou to w dou z dou x plus rho fx. Okay, so this is now being exact. There is no, there is no approximations that we have now introduced. This is what we have at this stage, which we can further simplify as minus dou p by dou x plus, so I will going to keep these three terms together. So mu times dou to u dou x2 plus dou to u dou y2 plus dou to u dou z2. So from here, I have split this term into two terms. So I get dou to u dou x2 plus mu times dou to v dou y dou x plus dou to w dou z dou x. So these are the other terms that we get. Okay, so I have clubbed these three terms, this term, and one term from here. And this is how I'm writing these three terms together. And you can see from this term, I can take mu. If I just look at this term, maybe I will just use a different color so that you know that we're not writing all the terms, dou by dou x. So we are now sort of saying that we can interchange the order of the derivatives, which you know can be done from your maths, okay, if the function is reasonably smooth. Okay, so that's a condition that you need. Okay, and so you can interchange here. So you get dou by dou x plus dou v dou y plus dou w dou z. Okay, so you can see that this term now is also can be set as 0 because of this condition here. Okay, so you can see that's another further simplification that you get. And therefore, if I put all these things together, I will get the following Navier-Stokes equation. So now putting everything together. So from here, this term is survives, this is the other term, this term is anyway 0, and of course fx term I should have taken out. Dou to u dou x2 plus dou to u dou y2 plus dou to u dou z2 plus rho times fx. So this is now the Navier-Stokes equation that we now have. Okay, and of course this is going to be the backbone of everything that is done in fluid mechanics. Okay, I will pause to see what are the questions.
Why have we neglected the line?
Why have we neglected the line force? Okay, so line force we will have to, so we can see that in this case, so it is not contributing to stresses, for example. Okay, so we saw that there is a stress term. Okay, that stress was the force per unit area, right? So if you have a force which is acting on an area, we multiplied, that is my stress, and to get to the force, we took that stress multiplied by multiplied by the area to get to the force. Okay, so this is not available in your with the surface tension.
That element may be the surface element.
But that's only a line element. It's not an area element. Okay, so it does not show up.
It can affect the overall.
It does affect the overall solution, but it enters to the boundary conditions. Okay, so we have not said anything about the boundary condition yet. Okay, so it is going to appear, it does affect the solution. Of course, we know the surface tension is a relevant force in fluids. It does affect, it can affect, in a lot of cases, it can affect substantially the fluid behavior. Okay, but it is entering not to the equation, but to the boundary conditions. Okay, so now, okay, other questions? So now if I look at the number of variables, just like what we had done earlier, so let me get rid of this side. So what are my variables? These 5 variables, all the 5 variables are there, or something can be dropped from here. Density can be dropped from here. Why? Because density is already said to be a constant. If it is constant, I know what is the value of the density. It's not always true, but let us say I also know what is the density. And I know at one point, and because it is incompressible, and I know it at all points. Okay, so I don't need to solve for it. So you can see I'm left with only four variables, which are u, v, w, and p. So these are my 4 variables. And what are my equations now? So the equations are now 1 continuity equation, 3 momentum equation, and that's it. So there is no equation of state that we have now. So we have 1 continuity plus 3 momentum okay, and no equation of state. Okay, now just to give you why there is no equation of state, just to sort of, so let us say if I look at pressure is equal to rho RT. Okay, so if I look at situation flow in this room, which is we know is an incompressible flow, right? And we are looking at isothermal, we can assume that, I mean, forget about AC, etc. I just take the room, turn on the fan. Okay, so there is no change in the temperature that we expect to get of air within the room. Okay, but what do we do? Do we know about pressure? We know pressure does vary about various points in the room. Okay, so you can see pressure is variable in this problem that we have talked about. Temperature is constant. It's an isothermal flow. And we said that rho is supposed to be an incompressible flow. So density is also constant. So you can see the right hand side is a constant, left hand side is not. And where is the problem coming from? Because this equation itself is not applicable. Okay, because the moment we say it's an incompressible flow situation, this equation is taken out. This equation is not applicable now. Okay, is this clear? Okay, so never use, so in an incompressible flow, don't use the equation of, there is no equation of state that is available to you. Okay. So you can see that this is the system that we are now dealing with. 4 variables and 4 equations. Now, if you were to put in the energy equation, that we will have temperature as an additional variable, and we will have an energy equation to solve along with that. So it will become a 5 variable, 5 variable and a 5 equation system. That is what we would get in that case. Okay. Now, okay, so now what we would like to do is now pause and look at this equation. This is our most important equation, and we are not even going to go to this other equation, okay, which is a more generic equation with all the compressibility terms included. Okay, so that form of the Navier-Stokes equation or the momentum equation we are not getting to. We are going to be using this form of the Navier-Stokes equation. So the first thing, as we had said, that the right-hand side of the Navier-Stokes equation is different in the 2 scenarios. One is compressible and the other one is incompressible. The left-hand side is exactly the same. There is a substantial change in the continuity equation, which of course allows us to get to a simplified form as shown here. Okay, that's first thing, that first remark. So we are making a few remarks about the equation. So we can also sort of start giving some physical name to this. What is the first term? So it's an unsteady term. Okay, what are these terms? These are my advection terms. Then this is my pressure force or pressure term. Then these are my viscous terms. And finally, we have the body force term. So the first thing that we would like you to understand is to recognize these terms, okay, physically, and say that, okay, this is what these various terms are. So now when we talk about a steady situation, steady flow, then what happens is the unsteady term will drop out. Okay, the partial derivative of anything with respect to time is 0 for a steady situation. So this is how you define of anything is 0, then this is a steady, under steady condition, this is what applies. Okay, so it's a partial derivative because we have introduced partial and total derivatives. We are sort of differentiating that we are talking about the partial derivative going to 0 for a steady term. Now, if I look at the pressure term, what is interesting about the pressure term? So it's only the pressure gradient which enters into the equation. So I'm not writing all these remarks in longhand, so you can make a note of that. Okay, so only pressure gradient is appearing. So what does it mean? So that means that pressure can only be found to an arbitrary constant. Okay, because I can always put some reference pressure, and with respect to that pressure, I know that the pressure here is this. I cannot find out what is the absolute pressure in my flow because there is no absolute pressure that I'm getting. I'm only getting a pressure gradient in my. So if I have to integrate this, then I will get a P minus P minus P ref, let us say. That's what I would get upon integrating this term. Okay, so P ref could be anything. So depending on what is the value of P ref that I use, I will get different values of P at different places. Okay, so that's the second remark that we can make here. We can also understand how many boundary conditions. So this is now the first time we are introducing this idea of boundary condition. So how many boundary conditions do we need to solve this equation? So 6, how do we arrive at 6? Okay, so how many, okay, what sort of an equation is this? Maybe let us ask this question first. It's a non-linear partial differential equation. Okay, so those are heavy terms. There are two heavy terms. One is a non-linear and the other one is a partial. First of all, we'll understand why is it a partial differential equation. So there are multiple independent variables. What are those multiple independent variables? X, Y, Z, and T. Okay, so we have X, Y, Z, T. Okay, interestingly, T, the momentum equation does not have a T term. Okay, it does have, you can see it is there in the compressible formulation. Okay, when we go to the incompressible, there is no variation of, there is no dou by dou T term. Okay, so that means that if you take whatever big size a tank and you push a fluid, if it is supposed to be incompressible, the same amount of fluid will go out from the other side instantaneously. Okay, which is a little bit odd, but okay, which is fine. Okay, because if I can keep on making the tank very big, very big, very big, very big, okay, and whatever I push in from one side, other side has to go out exactly the same amount, okay, at the same time, because I cannot change the density inside the system. Okay, so you can see that that's another assumption, that's another point where you can see that if the time becomes very big, somehow at some point of time, you would know that you will say that this information to propagate from one side to the other side will take some time, okay, and therefore this is no longer a incompressible system, right? So I'm just giving you examples where the velocities are not very large, okay, but you still cannot treat it as a incompressible system. Okay, so I'm just think of physical system could be like we have a pipeline running from the oil pipelines running from India to Iran, let us say. So what we are saying is the moment you put in whatever 1 liter of oil in Iran, exactly the same time, 1 liter of oil has to be delivered in India. Okay, do you think that would happen? Okay, so it's a very long system, very large system. You would expect now the compressibility effects will start coming to the picture here. Okay. So, okay, so so what we realize is that there are multiple independent variables, x, y, z, and t. And because we have derivative of each of these variables, we do get, this becomes a partial differential equation. That is what we have. Okay. Now, somebody said nonlinear. Now, what do we mean by a nonlinear equation? Yeah, so linearity versus nonlinearity essentially means that in linearity, superposition is applicable. Okay, so I can take several solutions and I can add them up, and that is also a solution. Okay, so whereas when we look at nonlinear, that is not case. Okay, but how do we understand nonlinear? Okay, if I double something, I would expect the output to double. My input, if I double the input, I would expect the output to double. Okay, that's like a linear system. If that is not happening, it's not a linear system. Another way to think about it, if I look at traffic, is it linear or non-linear? It's non-linear. And how do I know that? Okay, I can say that if I leave 5 minutes late, when I arrive 5 minutes late, okay, if I'm walking from here to whatever Hiranandani, I'm going to go from here to Hiranandani. I keep everything else the same. If I just start 5 minutes later, will I arrive exactly 5 minutes later there? No, may not be. Okay, maybe, may not be. Most of the time, I will not be. So you can see that's a non-linear system. That's a non-linear effect. Okay, so there are like two ways to think about it. One is if I double something, does the output get doubled? The other thing is if I shift something. Okay, so we are doing essentially y is equal to mx plus c only. Okay, we are going back to that equation with c is equal to 0, y is equal to mx. That's all we are saying. Okay, so if x is my input x is doubled, then y output y is twice. Okay, because it's equal to y mx system. And if I shift something, if I shift my x by something, my y will shift with the same amount. Okay, and in one case, in the other case, it will not. Okay, so it's essentially saying representing that equation and I mean, we are essentially saying they're talking about the representation of the same equation in different ways. So when how do I look at an equation and say it's linear versus non-linear? So we look at the dependent variable. Okay, so dependent variable is u here, and if we have dependent variable multiplying itself or dependent variable multiplying its gradient, okay, then we call that as a non-linear equation. Okay, and you can see that all these terms are fine. Okay, they have all these terms are fine. The only non-linearity is essentially this term here, the advection term. Okay, so that's what you need to understand and appreciate. Now, if I have to solve this equation, now I will go to the boundary condition. So we have already said non-linear. So I'm just noting down the key points, but that is all the discussion that we had. That I'm not writing it down. Non-linear partial differential equation. Now, if I were to just ask without having to solve, I mean, I'm not giving you the procedure how to solve it, but if I have to say that if I have to solve it, how many boundary conditions, how many integrations? So every time you look at it and you think that how many times integration is happening. So every time we know that there is an integration which is happening, I will generate a constant of integration. Okay, and that constant of integration I need to find out the values of that, which I will find out from the boundary conditions. Okay, so I know at this point, at this line along this surface or whatever, this is the value that the function or that variable that is taking. Okay, so then that's my boundary condition that I'm using. So here you can see that I have to integrate this equation. So this is where, so I start looking at it from the highest order term, highest order derivative that is available to us. So the highest order derivative is second. So it's a second order. If we can now add to this description of nonlinear partial differential equations, we can say it's a second order nonlinear partial differential equation because the highest derivative that is appearing in my equation is of order 2. Okay, and that means that we need to integrate it twice with respect to x. I need to integrate it twice with respect to y. I need to integrate u twice with respect to z. Okay, so I need to have 6 boundary conditions, as somebody said, with respect to u, but this is only with respect to u and only with respect to space. Okay, we'll also have to look at with respect to time. Okay, we'll also have to look at p, we'll also have to look at v and w. Okay, so you can now see that we need to, I'm not writing down how many equations, how many boundary conditions we need to have, but you can see that we need to have a lot of boundary conditions. Okay, just to sort of help you understand this point, let us say that I'm solving for an equation like a Laplace equation. Let us say if I solve for this, I hope that you would remember this equation. What is this equation? This is T, then this is a heat conduction equation. Okay, I hope you remember this. And if I'm solving it on a domain like this, okay, so I'm interested in solving, this is my Laplace equation. Okay, I need to find out, this is my domain xy. X is going from 0 to, let us say, A, y is going from 0 to B. Okay, so how do I solve this equation? I need to give what is the value of temperature here. Let us say T1, T2, T3, T4. Correct? So I need to prescribe what are the boundary conditions here. So you should be able to relate this. I hope you are able to relate this, right? Everybody can relate it. So I need to know what are the temperature at the 4 boundaries. If I know that, I can give you what is the temperature in this slab that will be arising. Okay, so and the governing equation that we are solving is this equation, which you can see is a part of all this. Okay, if I set so many terms, other terms as 0, I will be left with exactly what I've written here. Okay, so you can see that just like we need to prescribe 4 boundary conditions here. So if you can see that if I just look at this term, I need to have 6 boundary conditions for u that needs to be prescribed, and so on. Now, once you have understood this argument, I hope you will be able to appreciate how many boundary conditions we need here. Okay, understood? So the 4th point that we are talking about is on boundary conditions. Okay. Now, okay, any questions here before moving ahead? Yes, any question? Yeah, so nonlinearity has its own complexity in terms of how you will be able to solve it. But in terms of how many boundary conditions that you will generate, okay, you will only need one. You are only integrating it once. For example, if I just forget about these 2 terms and just look at this term, this is going to be half of u square and derivative of that with respect to x. So I can integrate it right away and I get half u square evaluated at 2 I mean, that one integration constant will appear now. Everything else is 0. Just for simplicity, I'm doing that. Okay, so this term itself will generate one. I mean, this is, as we said, the derivative of u square upon 2, derivative of that with respect to x. So integrating it will require one boundary condition to know exactly what my u square is. So yeah, so this is only x momentum equation, that is what we are looking at. You are also looking at y momentum equation, z momentum equation. What will happen in the y momentum equation? The second derivatives of v with respect to x and y and z will appear. Okay, so that means that you need to resolve these terms for v, you need to have 6 boundary conditions for v along 2 along x, 2 along y, and 2 along z direction, which will be enough to take care of these terms. Okay, so in terms of as far as boundary conditions goes, okay, it does not mean that the complexity of the problem is reduced or whatever. We are not trivializing the complexity of the problem here. Okay, just looking at it from the boundary condition point of view. So we have now sort of asking this question: is this equation applicable to turbulent flows? I mean, we don't need to define turbulent flows, although we will do that more formally. But if I say that, okay, turbulent flow versus laminar flow, is this equation applicable, or is there something which is missing here? What will be your answer? Applicable? Something is missing. What is missing? Okay, so that's why we did all this from basic steps. Okay, so please understand, did we make an assumption anywhere that the flow is turbulent? Did we make this assumption? No. So if you have not made this assumption, that means this equation is equally applicable to turbulent flows, period. Okay, if we were to say that this is applicable only to laminar flows, okay, then we have to make some restriction. No, this is where we are making a restriction. Where did we make that restriction? So that's why we are saying everything we are showing you explicitly, that this is where we are introducing non-Newtonian, this is where we are introducing compressibility effects, etc., etc. And this is how the equations will keep on changing. It's not that you cannot derive it for the most complex case. You can derive it for the most complex case. Okay, but here we are saying that this is applicable. We never said anything about laminar versus turbulence. This equation is equally applicable to a turbulent flow. Okay, so don't forget that. This is Navier-Stokes. It is applicable for all flows, laminar and turbulence. Okay, only thing is that this is the formulation is corresponding to Newtonian and it is corresponding to compressible. That's all. Understood? We will see where exactly the turbulence, why do we get additional terms, etc., in turbulent flows. That we will see when we will get to that. Okay, but this equation, there's absolutely no issues about it. Navier-Stokes is equally applicable to laminar flows as well as turbulent flows. Okay, now finally we can talk about coupled. So you can see why we call them as coupled equation. So what will be an uncoupled equation? So we have already said that there are 4 variables, 4 equations. So if you have one equation for one variable, A is equal to this, B is equal to C, this, C is equal to this, and so on. Then I can solve, I know what is A, B, C, and D. And okay, here, or if I have A plus B is equal to this, B plus C is this, C plus D is this, A plus D is this. Now you can see that I have now coupled them. I do not know whether if I just know what is the value of A, I cannot just give you readily the value of B and C. Okay, I need to solve these equations and then only I will be able to give you what is the values of the other variables. So you can see that a similar sort of a thing is involved here. Okay, I don't have a separate equation for U or V or W or P. Okay, I do have 4 equations, I do have 4 variables. Okay, but they are all coupled. Okay, so that's what we mean by a coupled equation. And coupling is sort of important when you actually try to solve it numerically in other ways. Okay, so you need to understand what does it coupling means and how does it complicate my situation. So here you can say that the 4 variables are coupled to each other. Okay, any questions here? I'm just trying to see if there is any other remark that I'm missing. So by that time you have time to think about and ask any questions, because this is sort of completes one of the most sort of central ideas of this course. Navier-Stokes equation, how do we get that, under what condition it is applicable, and what form is applicable where and why. But the only changes or any changes happening will be because of the consecutive relation depending on the correct. 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 And you have seen how exactly each of these are coming in. So, I mean, what I would like you to sort of say that, okay, from this point onwards, you just don't make a random statement. You have a very clear basis of what has been derived and why, and then you know that this is what is applicable where. Yes. So the pressure, as we have already said, that is only be determined to an arbitrary constant. So if I say that this is my pressure field, I can add a constant to that. That is also a valid solution. Okay, because if I put that pressure field into my Navier-Stokes equation, or my velocity field is correct, is the same. If I just take pressure field and add a constant to that, and then I put it into the equation, that pressure field, new pressure field, will also satisfy my governing equations, my Navier-Stokes equation. So I can add any constant that I want to that. Okay, so how does exactly the pressure is coming to the picture? Is a sort of coming in a very indirect way. Okay, so because you have raised this question, let us just discuss this. So you can see that pressure gradient is all that matters. So that means that if I'm talking about 1 bar here, 1 bar pressure is normally what we have, and vacuum, which is 0 bar. So I have 1 bar pressure difference. Okay, if I can take 100 bar and 101 bar, okay, that will have the same behavior. Okay, as 0 bar and 1 bar, because what matters is the driving force, which is exactly the same in both the cases. Okay, and absolute values are not important. But how do the absolute values come into the picture? Maybe through the properties itself. Okay, will my viscosity be different at these two values? Will my density be different at these two values of pressure? Okay, so if they are, then you can see that those constants which we are not talking about, they are actually appearing sitting as constants in our equation, but these values, the values of these things would change. Okay, so that's how the pressure is coming into an indirect way. It could affect the solution, or it affects our solution. Okay, but not as a direct way. Okay, finally, we can also remark that there are only two fluid constants which are involved. Fluid properties that are involved in my equations are only two, which are viscosity and density. Okay, so I think this is where we would like to sort of close our understanding of and move ahead and say, okay, now we understand how Navier-Stokes equations can be derived. So we will now introduce a new topic, tensors. So how many of you know what tensors are? If you don't know, it's fine. This is probably the first time maybe. So I expect a lot of you will be seeing it for the first time. If you are not, it's fine. Okay. So here we are going to talk about, we know about scalars, we know about vector. So scalar could be like pressure, temperature, and so many other quantities. Okay, energy, entropy, and so many other things. So what is a scalar? It has magnitude. What is a vector? Vector could be velocity, heat flux, and so many other things. So this has magnitude plus a direction. Okay, so now if you write it out like this, you realize that any physical quantity is going to have a magnitude. Okay, without magnitude, it is meaningless. Okay, so magnitude is always going to be there, but then you can have no directions in this case or one direction in this case. Now the question arises, can we also have a property, have a physical quantity which has two directions? And if I can think of, because I'm just sort of moving along this chart and moving down from 0 direction to 1 direction to 2 directions, 3 directions, and 4 on, and 4 and so on. Okay, with keeping the magnitude always in there, because as we said, magnitude is going to be the central to anything. So this is what we are going to call it as a tensor, a second order tensor. So this is going to have magnitude plus two directions, and we can say that this is can be even more, can even be more. Okay, now what do we mean by and how can something have more than two directions? So we have already talked about stress. So we said that stress is like force upon area, where both of these are vector quantities, force and area, and therefore the stress would have two directions, one corresponding to the direction of force and the other one direction corresponding to the direction of area. So, and if you, for example, if I look at a small element, area element like what has been drawn here, any question here? We have a question? So this element has a normal which is along this direction. So this is the direction of the area that we have, but the force can act on it along this direction, or along the third direction. Okay, and we have already know that it can have different effect on this element here. In one case, it may want to pull it. In the other case, it is trying to shear it. Okay, so you can see that I'm not changing the area element. All I'm changing is changing the direction of the force. Okay, similarly, I can go, instead of this area element, I can go to an area element which is perpendicular to this. So now I can see that I'm talking about this force. This is the normal to this area. And I can have force along this direction, as well as this direction. Three directions I can have the force which is applicable to that. Right? So again, now what I'm doing is I have changed the direction of the area, okay, and the forces are now being different. Again, one is trying to shear, or two of them are trying to shear this element, and one of them is trying to stretch this element. Okay, so you can see that again that has a different sort of an action compared to whatever action was happening here. Okay, and we have already drawn the cube and the six sides, and we have said that this is the type of force balance, etc., that you would have. Okay, so we are going back to the same idea and saying that this element, when we look at stress, we do need two directions corresponding to the direction of the force and corresponding to the direction of the area. And we said that we are going to use two subscripts. One was, let us say, if you are using x and y, so this is the direction of the area, and the other one is the direction of the force. Okay, so this is what we sort of know. I mean, I hope that you understand this from your basic understanding of fluid mechanics and heat transfer, or fluid mechanics and solid mechanics from the previous courses. Okay, so this is what I would, this is like our starting point, and we will move ahead from here. So we will see that how do I first say what is a tensor, how do I define the second order tensor, how do I create a second order tensor, can we create, how do we create tensors of higher order? So some of them we will be doing in a little bit of abstract or mathematical sense, that okay, this is what these ideas are, and then we will see that we can keep on relating them to some of them. I mean, just like the second order tensor, we said stress is like a second order tensor. Okay, so we are able to sort of relate what are the two directions as the direction of force and the direction of the area on which it is acting, and so on. So sometimes we will be able to correlate the two, and sometimes we will say, okay, this is a third order tensor, fourth order tensor. There is hardly any physical meaning that I can give to you like that, but of course it is a generalization of this idea. Okay. And of course, this ideas of tensors is very important. Tensor notation is very important. It helps. We have just derived the Navier-Stokes equation. Just we have seen that this is such a long equation, but we can write it out in a much simpler form, okay, using tensor notation. So that's like the very simplest of the reason why we would like to understand tensors. Okay, just it makes our equation writing, manipulation, other things more easier. But there are other benefits which, as you keep going along using more and more of tensor notation, you will be able to appreciate that. Okay, so that's where we will start off with our discussion. So, okay, any questions before starting on anything that we have said? So, interestingly, so even before getting into tensors, we will go back to vectors. Okay, and we have done a lot of vector algebra, etc., a lot of things that we know about vector. But one thing which we have never done is what is a vector? How do we define a vector? Okay, so we say vector has, so we say it's a property of a vector is that it has magnitude and direction. Okay, but anything which has magnitude and direction, will it become a vector? Okay, so this is the first question that we will answer. Okay, and so this is the first time formal definition. What is a formal definition of a vector? And how do we test if any quantity is a vector, is indeed a vector or not? And once we understand how to define a vector, we will be able to define if the quantity has more than one direction. We are basically seeing how to handle the one direction. If we are able to handle one direction, we will be able to handle multiple direction by a straightforward generalization of whatever we are going to talk about. So how many of you know what is the definition of a formal definition of a vector? Anybody? Yeah? Not really. But what is a physical quantity? How do I define a physical quantity vector? I just give you a physical quantity. I give you a quantity. I say this is the direction. I'm moving in this direction. Is this now is this a vector or not? I have a direction and I have a magnitude. Okay. So we will see how to define a formally. So what we do is look at the rotation of a coordinate system. So let us say I have this coordinate system and we will do it a rotation about the z-axis. So 1 and 2, you can think of x and y directions. And then we are going to rotate this coordinate system. So this becomes 1 prime and this is now 2 prime. And let us say that I have any physical quantity, any quantity here. Okay, this is indication. As we know, vector can be represented with these components. So if I'm just saying that these are the components that we have, in one case the components are whatever component I get here and whatever component I get here. In the other side, I get this as the components. Okay. So now, if these components are related to each other in a certain manner, then I will call that quantity as a vector quantity. So that's a formal definition of a vector. So in this case, so let us start defining certain angles. So I will define an angle beta, and I will use two subscripts, one and okay, let us say, let me just define beta ij. So beta ij first, I'm going to define it as old I, and this is my new j. Now let us understand this clearly, what exactly we are talking about. So we are saying that we have 4 lines here, as you can see. Okay, there is certain angles between these lines, of course, which is 1 and 1 prime can make an angle. Okay, 1 and 2 can make an angle, 1 and 1 prime can make an angle. Okay, and similarly 1 prime can make an angle with so many other things. Okay, of course with 1 and 2 I'm not interested, 1 prime and 2 prime I'm not interested. I know already these are rectilinear coordinate systems, so I know they are already fixed to 90 degrees, but the other angles I can have. Okay, so I can have 1 and 1 prime, I can have 1 and 2 prime. Okay, I can have the angle with respect to 1 prime and 2 with respect to 2 prime. Right? So if I have to write it down, so I have beta 1, 1, which is this angle here. Okay, and then this is my angle, this is another angle that I'm making, which is beta. And how will I write it? I've already said that I will write it in old I and new j. Okay, so this is my angle beta. Old is 1 and new is primed with primes. Okay, understood? So old is 1 and 2, new is 1 prime and 2 prime. Okay, so my angle beta, this I will write it out as beta 1, 2. Right? Now similarly with respect to, so these are the two angles that I would have with 1. Now what are the two angles that I will have with 2? I will have this angle, which is beta 2, 2. Okay, so, and I will have another angle which is 2 and 1. Okay, old 2 and new 1. Okay, which will be angle my direction I need not show. Okay, but this is my beta 2, 1. Old is 2 and new is 1. Right? So this is the nomenclature that I'm going to use. Okay? So I'm just using again for beta, which is the angle between the two things. Here it is, because we are doing a very simple rotation. Okay, because we are simply rotating about the third axis. Okay, this beta 1 is equal to beta 2, and you can say, oh, why am I making all this first? Everything is known. Will you give me one angle, every other angle is fixed, which is right, which is correct in this case. Okay, I know that beta 1 is beta 2 in this case, and beta 1 is nothing but pi by 2 plus beta 1, and this is nothing but pi by 2 minus beta 1. So I only need one angle, everything else is known. But just think of it that I am doing not just in a planar rotation, but I can do a more complex rotation. I can rotate the axis one with respect to the other in whatever way I want. And then I would have a lot of angles and I will have to worry about them. So keeping that in mind, we are using this more complex notation. Okay. And so again, with respect to 1, you can see that there are two new axes with 1 prime and 2 prime. So old is 1, still 1. So I will call this angle as between 1 and 1 prime as beta 1. And between 1 and 2 prime, I will call this angle beta 1. Okay. And similarly with axis 2, I have now new is 1 prime, or it could be 2 prime. So I will have again two angles, beta 2 and beta 1. Okay, understood? So I have 4 angles that I'm talking about. Now what we can show is that if the coordinates of this is x1 prime, x2 prime, then how will they get related to x1 and x2? You can show that this is related to cos beta 1, cos beta 2, and cos beta 1, and cos of beta 2. Okay, so I will leave this as a small exercise. You know that if I just take this vector, if this is a vector, position vector, I am now interchanging, although I'm trying to define, but I'm just saying that, okay, this is how it will transform, and we know that this is how it will get transformed, and you can plug in these angles. So the only difference is that we have done it in a more generic form, okay, rather than with just one angle. This is cos. So if you remember the transformation matrix, it is minus sine alpha and sine alpha, and in fact, this should be plus, and this should be minus, and this should be cos alpha. That's what you would get. Okay, and which is essentially coming right away from here. But as we said, in general, the angles may not be that simply related. So we are trying to do it in a more generic way. So this is, so what I'm saying is that this is the relationship that we know will get satisfied if it is a position vector. Okay, and this is and now from here, so what we are now going to do is from here we are going to see how to generalize this. Okay, from a 2D, right now we are doing in 2D, and we are doing a planar transformation that we want to do with all 3 components. Okay, my vector is somewhere pointing in somewhere in space, not just along one plane. Okay, and the coordinate system is also rotated about some arbitrary angle, about some arbitrary axis. Okay, so then how do I write out all these angles? So you can see that if I just follow this logic, once I understand this logic, I can find out that and this is something for you to show. Okay, please show this as a small homework. You don't have to submit it in. Okay, but you please show this for yourself so that you are very convinced about what we're talking about here. Okay, and we are not able to show it in a more generic thing with just too much math without any value to it. So we will not bother about that. So we will get it as, and we are now going to use a shorthand. Okay, so we know that causes are involved. So let us just say that instead of cos writing it as cos beta ij, I will write it as simply Cij. It's just a shorthand I'm going to use. Okay. So this is fine. So now I can, if I were to just write it out, I can in 2D, this is cos 1. Okay, so let us just write it out with C's in there. This is C11, this is C21, this is C12, and this is C22, and then X1, X2. So you can see that this C's using C's instead of cos has made my life so much easier. Is it time already? No. So using the C's has made my life so much easier. Okay, and it is nothing but defined as cos of beta of these angles. And now if I want to generalize it to 3D, then I will write it out as, let me just write out in this itself. I will write out with the C, what term will come here? C31, C32, and then here I will get C13, C23, and C33. And this is going to be X1, X2, X3. Okay, so you can see that this is where C's now are the angles between, again, old I, Cij, is the cos of the angle between the old I and the new j. Okay, so now you can see that this is how the formal definition, this is now the formal definition of a vector. So we have done it for one, because knowing that this is a vector, we know that this equation will get satisfied. Now we can say that any vector which satisfies this equation will be called as a vector. Okay, so that means that what does it mean? How do we use this information practically? So I say that, okay, if I claiming that this is a vector, okay, people say time is a vector, it's not a vector, you can resolve it. You can resolve it in this manner very easily. Okay, you can say that if time is a vector, okay, then let us take some arbitrary coordinate system. Okay, I can have the components of whatever that physical quantity is on that coordinate system. Now I rotate that coordinate system by an arbitrary amount. Okay, okay, and then I know that for a vector, it should satisfy this component. So I now look at the new components that has been generated in the new coordinate system by that arbitrary component, by that arbitrary quantity. And if the components are satisfying this rule, then I will call that as a vector quantity. If not, I will say that that is not passing my test, and sorry, I will not call it as a vector quantity. And you can see time is not going to satisfy this, for example, very clearly. Okay, where always people say, oh, there is a direction, there is a magnitude, so why is it not a vector quantity? Okay, you can talk about current, so many other things. Okay, some seems to have a direction, but is it really transforming in this manner? Sorry, it does not. Okay, so those which will not transform will not be called as a vector quantity. Okay, is this understood? So now once we have understood this, we can see that if I have two directions, then what will I going to do? So this is now like my transformation matrix, okay, which is taking it from one coordinate system to the other coordinate system with one directions. Now if I have two directions, I will have to do it for both the two directions. Components can change around both directions. Essentially, it means that I have to multiply it by two times. Okay, so I will have this matrix twice appearing twice. Okay, is this understood? Okay, now this is where the tensor notation will start becoming useful. Now we say, what are we talking about? Is it the same matrix? I just multiplied twice. It's just a square that I'm getting, or is it something else? So this will get clarified now once we introduce the idea of tensors. Okay. Any questions here? So to introduce the idea of tensors or a tensor notation, maybe first we will start off with this equation itself. So what is this equation? If I have to write out x1 prime, it is simply c11 x1 plus c21 x2 plus c31 x3. Right? So how can I use some sort of a shorthand to write out this equation? Okay, this is, I mean, you will see that this is all that needs to understand the idea of a tensors. Okay, so please pay attention to, it's a very few simple steps that we will do, and suddenly we'll make a very big statement. Okay, so we'll have to understand what is the basis of that. So you can see if I have to write out this equation in a more generic form, I can write it out as C1 X1 sorry. So you can see that this is what is common. This subscript is common. Okay, so I can write it out as C1 and this is my I here. And this I is going from 1 to 3. Right? Now similarly, if I have to write out the second equation, how will I write out the second equation? You can see that it is going to be, okay, let us just write it out, C12 X1 plus C22 X2 plus C32 and X3. So how will I write out this equation? Is again Ci2 Xi, I going from 1 to 3. Correct? So this is how I can write out the second equation. And similarly, my third equation is summation of Ci3 Xi going from 1 to 3. Correct? Can I write these three equations together? So what I realize now, I've already realized that this first subscript is common between these two, okay, common between these two, and essentially there is a summation of these three terms. So there are three terms if I write it out. So I have summation of three terms that gets involved here. Now the other thing which I realize is that whatever is a subscript here is a subscript here. Whatever is a subscript here is a subscript here. Whatever is a subscript here is a subscript here. Correct? So if I have to write out in a more generic form, can I write out this xj prime is equal to summation of C of ij and xi, I going from 1 to 3. Right? So I just say that, okay, this has exactly the same information that is there here as well. Okay, I will say now take j as 1, take j is equal to 1, you generate this equation. Take j is equal to 2, you generate this equation. Take j is equal to 3, you generate this equation. Correct? Right? So you know that you can generate all these three equations by simply taking three different values of j's. So if I now look at the indices, there are two types of indices we have introduced in the process. One, which was I, and what was interesting about I is we need to add up over I. And why, and how do I know that? Okay, because I is appearing twice. It is appearing C1, Ci1. Now I'm looking at it from a different point of view. These equations that we have written, I'm just looking it back and said, what were I doing? What were I doing is that I'm simply looking at this I is appearing twice, and if I is appearing twice, I was simply adding it up over this I. Okay, so I will call this as a repeated index. I is appearing twice, is getting a repeated index. Now, when I write it out as this, j, is j appearing twice? No, j is only appearing once. So I will call this j as a, so I is my repeated index and j is my free index. I can of course choose, instead of I and j, I can choose R and S and T and M or whatever. Okay, it's not that I will always be free, repeated, and j will always be free. It's just in this example that we have taken, this is how it has turned out to be. And when it is repeated, it means that I need to sum it up. Okay, and free is free. I can choose different values of j and I can generate a whole set of equations. Okay, so this is where I think we will stop because of lack of time, although we would have liked to finish this topic. Okay, but we'll have to stop here and come back in the next class and we will pick it up from here. So we are still to introduce the crux of the matter yet, but all we have talked about, so what in summary, let us just summarize what we have talked about in today's class. We have talked about driving the Navier-Stokes equation by putting the constitutive relationship into the Cauchy's equation, and we saw that where compressibility and incompressibility effects come into picture, where Newtonian versus non-Newtonian, etc., comes into the picture. And then we saw that if I look at Newtonian fluid and incompressible flow, then I would have the Navier-Stokes equation, which looks like this, whatever was written earlier, which has certain properties. These are second order, non-linear, coupled, partial differential equation. Okay, and we need a lot of boundary conditions to solve for them. Okay, we also realize that uh, the pressure will always be in terms of gradients and so on. So that is what we have seen. And then we went in from there to tensors, and we said that in tensors, when we talk about vectors, there's a formal definition, which is when you take the components of that, and you also go for a coordinate system which is rotated, look at the components in the two cases, and then if the two components in the two cases satisfy a certain relationship, okay, then only we call that as a vector. Okay, and then we said that we are going to generalize that idea further on for if you have two directions, which is what we are trying to do next. Okay, so this is where we will pick up from the next class.